Alright, class 12, the topic that we are going to discuss today is something called self-induction. Now, what is this phenomenon? Let us see. So, what we have is, we have a coil which of course is connected to a power source, alright, and then say we have a variable resistor connected to it. This is the variable resistor. It could be a resistance box or it could be a rheostat. Now what we do is, okay, let us say we also have a galvanometer or an ammeter here. Alright, these components are not necessary. What is more important is, by varying the resistance over here, alright, what we can do is, we change the current that is flowing through this loop or flowing through this coil. So when we are changing the current which is flowing through this coil, what happens is we are also changing the magnetic flux that is linked with each turn of the coil. Alright? Because current flowing generates its magnetic field, of course we know that. So therefore there is magnetic flux linked with each turn of the coil. So when we are changing the current, we are changing the magnetic field and thereby the magnetic flux. Okay? So whenever there is a change in magnetic flux linked with this coil itself, alright, according to Faraday's laws, what happens is there is an induced EMF since the magnetic flux is changing. And if the original current, this current is flowing in this direction, as you can see, towards our right hand side, okay, the induced EMF or the induced current will be such that it wants to oppose the cause producing it. Okay, so to say, the cause that is producing it is current basically flowing towards our right hand side, so current will be induced to the opposite direction. This induced current or induced EMF tries to decrease this value of current. So if phi B, phi subscript B, the mag is magnetic flux linked with each turn of the coil, okay, linked with each turn of the coil, alright, and capital N be the number of turns in the coil, then what we have is the flux linked with the coil. N phi B is the flux linked with the whole coil. Alright, so the flux linked with the coil is directly proportional to the current flowing. The more the current flowing, of course there will be more flux linked with the coil. So I is the current flowing, so to say. Or from here we can write N phi B is equal to, obviously we know the proportionality sign can always be replaced by an equal to sign provided we add some constant. And the constant here is denoted by a capital L. So capital L into I, where capital L is called the coefficient of self-induction, or it's also called self-inductance. Capital L, let me write over here, is called coefficient of self-induction, or it's simply called self-inductance. Do remember this relation. From here, of course, we can write L is N phi B divided by I. So this is your self-inductance or coefficient of self-induction. Now, from this relation itself, therefore, we can define our coefficient of self-induction or self-inductance to be the flux linked with the coil for unit current flowing through the coil. That is how we define our self-inductance. Now, there's another way to define self-inductance. Okay, let us give a look at that. 2. So I'm erasing this part. I hope you will have copied all of these things after pausing the video, of course. Okay, now if E be the induced EMF in the coil, of course, okay, then we can write, according to Faraday's laws, E is minus M delta phi B by delta T, where delta phi B, of course, is the change in flux taking place in time delta T, or E is equal to minus delta N phi B divided by delta T, or E is equal to, now see, N phi B, from this equation we can write, instead of N phi B we can write L into I, so minus delta Li upon delta T. So from there what we can write is, we can write E is equal to minus L delta I upon delta T. Since L is a constant, so therefore it comes out of the delta sign. Self-inductance is a constant, mind you, so therefore it comes out of the delta sign, and from here therefore we can write L is equal to minus E divided by delta I upon delta T. Alright, so how do you define self-inductance or coefficient of self-induction from here? What we can write is, coefficient of self-induction or self-inductance is the EMF induced in the coil for unit rate of change of current flowing through that coil. So that is exactly what we can write. Alright, what we now want to do is, we want to find the self-inductance of a long solenoid. So we have a long solenoid over here, through which current I is flowing at any instant, say for example. Now L be the length of the solenoid, A is the area of each turn of the solenoid or the coil, and capital N is the total number of turns in the coil. So small n, which is capital N upon small l, is what? It is the number of turns per unit length. So the magnetic flux inside the solenoid will be how much? It will be B, which is mu naught N I, where N is the number of turns per unit length. Remember, we've already found this out. The magnetic field at any point inside the solenoid using Ampere's circuital law. Don't forget that. This is one of the applications of Ampere's circuital law. Or, in other words, we can write B, the magnetic field at any point inside the solenoid, to be mu naught capital N upon L into I, because small n is capital N upon L. So therefore, what we can further write is, the magnetic flux linked with each turn, of the coil will be how much? Will be phi B. Let's say it's phi B. Okay, so phi B will be how much? B into the area. Okay, this is what magnetic flux is. So thereby this becomes mu naught N upon L A into capital I. This is the magnetic flux linked with each turn of the coil of the solenoid. Alright, now since the coil or the solenoid has capital N number of turns, so what will be the flux linked? You can copy this. Alright, so I believe you've already done that. So I'm erasing this. Class-12. Alright. So, therefore, the flux linked with N turns of the coil will be how much? It will be N phi B. This is the flux linked with N number of turns. So therefore this becomes equal to mu naught N squared upon L capital A into the current flowing through the coil. Thereby, what is the coefficient of self-induction or self-inductance of this coil? Therefore, self-inductance or coefficient of self-induction, I am not writing that because it's lengthy. Alright, so self-inductance of the coil is capital L, is noted by capital L. Okay, let me erase the lower half. So capital L will be how much? N phi B according to definition divided by the current. Okay, according to the definition of coefficient of self-induction, we have this. So thereby, this becomes equal to mu naught n squared upon L into A, or L is equal to mu naught n squared upon L into A. So this is the expression for the coefficient of self-induction, or so to say self-inductance of a given coil, mu naught n squared upon L into A. And you can see from this expression that more the number of turns of the coil, more will be the self-inductance of that particular coil. Likewise, more the area, bigger the area, more the self-inductance, and more the length, longer the solenoid or longer the coil, more will be its self-inductance. Alright, so for a given coil, for a given solenoid, having a certain length, certain area, it will have a given value of self-inductance. So for that particular coil, the value of self-inductance is a constant, remember. Furthermore, if this coil is wound on a certain material which is acting like a core, so we have a core over here of a certain material, and the permeability of this material is mu. Okay, so in that case, if the coil or solenoid is wound on or over a coil, over a core of permeability mu, then what will be the self-inductance in that case? The self-inductance L will be mu and not mu naught. Mu naught is in the case when we only have the coil. We don't have a core substance, so to say. So when we have a core substance whose permeability is mu, then L is mu n squared upon L into the area A. So this is the expression for the self-inductance. So you can see self-inductance is also dependent on the material of the core, so to say.